The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon and good morning, everyone. I trust you're all surviving this new era. This next series of this presentation is going to be a protection differences, overcurrent relays in instantaneous mode versus an arc flash relay. I was struggling trying to find data for this, not necessarily data, but information to fill my slides because it's such a simple topic, and we're going to try to discuss it. So bear with me. I don't think we're going to take the full hour to discuss this. So just as a reminder, time is directly proportional to incident energy. That's right here. So time, whether it's 600 volt, 27, 14, 3, or less than 600 volts, time is directly proportional to incident energy. So if you double the time, you double the incident energy. The longer the time, the fault duration, the higher the incident energy. And this is directly out of IEEE 1584. So basically what we're trying to show is whether an overcurrent relay in instantaneous mode is faster than an arc flash relay. But there's a couple of other things to take under consideration when you do that, because a relay in instantaneous mode may not be properly coordinated to function in your setting. Just a recap of CSA Z462 and NFPA 70E. The 8 methods of mitigating arc flash. Zone selective interlocking, obviously. Zone selective interlocking removes the time delay intentionally placed in the relay to allow a properly coordinated system. So coordination is very important. Obviously, if you have a properly coordinated system, the protective device closest to the fault will operate clearing the fault. That means basically that any device further away or closer to the source has an intentional time delay in it to allow the protective device closest to the fault to operate. That also means that closer and closer to your source, energy levels get higher, time delays get longer, unless you use something like zone selective interlocking, which removes the intentional time delay. Differential relaying is basically looking at a zone. So think of your main switchboard coming in. You measure the current coming in, you measure the current going out. If that is equal not to 0, then you have a fault inside that board, and we have to trip right away. That's really a good system because it's looking at a zone. You're not sacrificing coordination for arc flash protection or arc flash mitigation, because if the current coming into the board doesn't equal the current exiting the board, then you have a fault within the board, and it may be an arc flash or will be an arc flash. Zone selective interlocking does interfere with some coordination if it's not done right. Energy reducing maintenance switch. An energy reducing maintenance switch is basically what this topic is about. What we're trying to do with the energy reducing maintenance switch is reduce the instantaneous pickup to its bare minimum. And when it's at its bare minimum, you may sacrifice coordination for safety. But at the time that a person is working on the cell, it is more important to protect that worker than coordination. So that person could be working, an electrician, qualified person could be working on your switchboard, turn on the energy reducing maintenance switch, and then if you have a large motor starting up downstream, it may be possible for that maintenance switch, which turns your protective device to a really low instantaneous pickup, will activate. Energy reducing active arc flash mitigation system. This is probably one of the only systems that can probably reduce your arc flash or your current time, your time to clear the fault lower than the operating conditions of the switchboard or the protective device. So if you have a 5-cycle breaker, you can probably operate your protective equipment or reduce the incident energy to something below 3 cycles if you have a 3-cycle breaker. So we're playing with time, but you're trading an arc flash event to a bolted fault event. So there's some hazards that need to come into play. Arc flash relay, which is also what we're going to discuss here. So we're going to be comparing arc flash relay with the energy reducing maintenance switch, basically instantaneous protection. High resistance grounding, I don't know if you remember my my presentation from, seems like a long time ago, but high resistance grounding does not reduce incident energy. And I catch myself a couple of times because we've actually produced a high resistance grounding system that will allow a user to reduce incident energy because we've implemented an arc flash relay with it, and that was our smart HRG system. So not all HRG systems are created equally. You can have some HRG systems that can act as an arc flash relay as well and reduce the time that the fault is on the system. When I mentioned this before, it was misunderstood. So trying to make it clear now, HRG by itself does not reduce incident energy. HRG with an arc flash relay, which we have in a smart HRG system, will reduce incident energy because we're detecting the flash and reducing the time that the fault is on the current. Current limiting fuses, obviously, if you're in the current limiting range, they're going to operate in a quarter cycle, but they're not going to cover the entire current ranges that you have. Shunt trip relays, obviously, if it's connected to a arc flash relay, it will operate and clear your fault. So the schematic that I used in this particular example is basically very simple. With 12.4 kV coming in with the utility, going through a fuse, transformer, and we're looking at the low voltage section over here. So we're going to concentrate on the low voltage section. So you have T1, transformer. Transformer is shown as solidly grounded, but is actually resistance grounded. But as far as arc flash mitigation is concerned, according to IEEE 1584 2018 edition, the grounding of the transformer bears no difference to the incident energy. Circuit breaker number 4 going to a bus, and circuit breaker number 5 protecting a motor. Very, very basic. We're going to put a fault on the bus, and we're going to rely on the instantaneous protection of circuit breaker number 4. Unfortunately, circuit breaker number 4 is set up for 12 times instantaneous. No, sorry, we have no instantaneous on this one. This is an example of the circuit breaker under short circuit. No I, only LS. LS if it's high resistance grounding, LSG if you have a solidly grounded system. There is no, you don't necessarily need a G function on a circuit breaker if you have a resistance grounded system. So if you have a fault on bus number 2, it's going to take 160 milliseconds to clear that fault. You have a fault clearing current at the fault clearing time is 18.4 Ka. Your incident energy is 11.294 calories per centimeter squared. And I'm just showing you what the difference is between a non-instantaneous and instantaneous. And you can see here that we operated the breaker under the short-term rating. So we turned on the instantaneous. However, I've selected for this example 12 times instantaneous, 12 times pickup. It's still going to operate in 160 milliseconds because the 12 time pickup is 38.4 kV and we've got 18.46. So although we have instantaneous, the instantaneous is set so high, it might as well not even be there. So you have to have a properly coordinated system and still have 11.294 calories per centimeter squared. So I've lowered the instantaneous now to 6 times. Well, 6 times we're just barely at the start of the instantaneous pickup, and we're at 19. 6 times pickup is 19.2 Ka, and we're at 18.4. 18.4 is still less than 19.2, so we're still at 11.294. So we tripped on this breaker on short time. We didn't trip it on instantaneous. Going to 4 times Ka, 4 times instantaneous. Now the pickup is 12.8 Ka, and we can see that we've actually picked it up on instantaneous over here, and we operated the breaker in 71 milliseconds. Still had a fault current, arcing current of 18.4 Ka. However, our incident energy, because we operated in 71 milliseconds instead of 160 milliseconds, is now 5.006. So 5 calories per centimeter squared. We can lower our instantaneous even further, 2 times. And what happens at 2 times is we trip in 70 milliseconds, so we save 1 millisecond, but we may sacrifice loads that are downstream. And we're at 4.941 calories per centimeter squared. And these are all at 18 inches. So to introduce arc flash relays to compare against these, we're going to compare our Architect relay, which has 12 light inputs with built-in test when you have the point sensor. It's configurable to light only, light and current, light and pressure, has 3 or 4 discrete inputs from external sources, outputs, 4 discrete configurable contacts, 1 or 2 discrete outputs. And the reason why I have 1 or 2 and 3 and 4 is one of them can change from input to output. So it's got 12 inputs that you can see here and here. You can interlock it with current with the CT, and we have a 5 amp and a 1 amp input. These are the inputs and outputs, and the output relays here. So 3 normally open, 4 normally open, and 2 changeover. We also have the Sentry relay. The Sentry relay has 3 light inputs. And for every light input, there is a distinct output contact. With that distinct output contact, if arc flash number 1 input picks up, we energize output number 1. If flash number 2 energizes or witnesses a flash, we can close the contact for output number 2. And if arc flash number 3 comes in, we can close output contact number 3. This cannot be interlocked with current. However, we can interlock it with pressure. And this particular relay is also a ground fault protection relay and replaces our MGFR line of relays with the dip switches here. So we've replaced all the ground fault relays with the MGFR, 9 models with 1 of these So you can have multipliers of 0 to 1,000. So you can get ground fault protection from 100 milliamps to 1200 amps with this relay. If you combine it with our HMI, you have an infinite number of ground fault pickups that you can choose from. Right now, it's a direct replacement for the MGFR, provided you choose the right multiplier. But this relay allows you to basically segregate where the fault is. So, say, example, you have a ground, you don't have a ground fault, but you have a 3-high section of circuit breakers. If you have a light sensor going to the back of the cable compartment of the top breaker, you can trip only the top breaker if you witness a ground or arc flash in that compartment. And this is for metal clad switchgear. Middle compartment will be arc flash relay number 2, and we can close or open the circuit breaker in position number 2. And if you had arc flash in cable compartment number 3, you can open the bottom circuit breaker. For the main bus, we can do that with another relay. We've had one customer that used this to monitor the line side of the main breaker with one arc flash relay, monitor the main bus with the other arc flash relay, and the difference being that if you have a fault on the main bus, you can open up the main breaker, but if you have a fault on the line side, then you can open up the upstream breaker. And this is important because all the studies that I've looked at, 4 times out of 5, the highest incident energy is always between the transformer and the line side of the main breaker. And we can show an example of that later. This particular relay is an answer to the questions from our customers that said, I like the HRG system, but I want to have the ability to lower incident energy. So we developed our arc detection module as part of the DSP system. So the DSP system, when used with the arc detection module, can lower incident energy if the fault, arc flash, is within the gear that you're monitoring. If it's outside the gear, you will need something else. So it has 7 light inputs, either fiber or light sensors, 7 pressure inputs, so you can interlock it with pressure, and you use exclusively with a DSP HRG system. 1 discrete output. These outputs over here are going to trip the main breaker because the fault is going to be downstream of that breaker. Here's our pressure sensor. Available pressures, a factory set of 0.4 bar, and it probably takes about 10 milliseconds to operate this particular device. This one has 2 normally open and 2 normally closed contacts, and it can go directly into these sensors right here and have pressure pickup. Again, it's a mechanical device, so it's going to take about 10 milliseconds to operate. So with the pressure relay, because of the 10 milliseconds to operate, if we put an arc flash on the bus, we're going to trip in 60 milliseconds. So obviously these are 3-cycle breakers. 60 milliseconds because you have 10 milliseconds to detect the presence of the fault and 50 milliseconds to open up the fault. Unfortunately, we can't show you that, so I showed the line over here where the 50 milliseconds or 60 milliseconds is, and we have 60.2 milliseconds, and that's how much time you save. So that time savings reduces the incident energy to 4.553 calories per centimeter squared. As far as optical is concerned, we have several types of optical sensors. We have the optical point sensors, which are wired, because we've got some feedback from our customers that says they like the fiber. However, it's difficult to accommodate the fiber when dealing with shipping splits. So we've come up with a point sensor which is totally wired, and that's what the point sensor looks like. And you're looking at an area, and it's the area is 3 meters by 7 meters. So it's great for metal enclosed and metal clad type of switchgear. We have a fiber point sensor as well. So we have a fiber point sensor with wire, a wired point sensor and a fiber point sensor. And all we're doing here is we're sensing the fault at the light sensor here and transmitting that light back to the relay to detect the presence of the fault. As you can see, the wire is quite delicate, and that's why some people may not like to use fiber when you have a lot of shipping splits. Or we have the point sensors, which convert to a fiber input for shipping splits if you want to use the fiber. The fiber we have is either open clad, closed clad, which is what we have here, or open clad when you don't have that black protective sleeving over the fiber, so you can wrap it around bus if you want and use this device to bring that signal back to the relay. So now when you have a arc flash with light, we're down to 3.87 calories per centimeter squared, and we tripped in 51 milliseconds. It's hard to see, but we tripped in 51 milliseconds. And 51 milliseconds is right there. So we saved a little bit more time. So to summarize, the light sensor at 51 milliseconds, we have 3.87 calories per centimeter squared. The pressure sensor, an additional 9 milliseconds, 4.553 calories per centimeter squared. At 2 times and 4 times instantaneous, we're basically at 70 and 71 milliseconds. So you can see that they're very close together. And anything above 6 times, we're at, we pick up on short time, so it's 160 milliseconds. And we're at 11.3 calories per centimeter squared. So now I'm going to show you a live example, and we're going to see if this works. There we go. So we're going to put an arc flash, and this is courtesy of my good friend Albert, who was kind enough to let me borrow this this file, and because I didn't have enough time to learn how to use this, and I'm going to make a lot of mistakes. So sorry, Albert, from ETAP. So we put a fault on the line side of this particular breaker. You can see that we haven't operated the fuse on the line side. We've operated the circuit breaker that's above that, protecting that. And you normally don't have that circuit breaker up there. So you can see why it takes so long, or why the incident energy in this particular leg from between the main line side of the circuit breaker and the transformer is high incident energy, because we're relying on protection from the transformer to clear this fault, and it takes a long time. So we're at 332 milliseconds, 43.215 calories per centimeter squared. We've implemented some protective measures with some of our OEM customers who put a reclosure up here, and with that reclosure, you had an arc flash relay here, and you interlocked it with pressure, operate that arc flash or reclosure to actually lower this down to a reasonable level. So again here, we can put in our architect relay, and we put in the architect relay. You can see that we have 12 inputs that we can put in. We can interlock it with current and pressure, or have light only. For the sake of argument, I'm going to go with light only, and we use some fiber sensors. This one, point sensors. And if I put a fault on this bus, we would trip that in 51 milliseconds. And this is a different example from what we had before. So our incident energy is 6.6364 calories per centimeter squared. Please ignore this level C because that's the software puts this in and it's user alternative, or you can change that to user level. So we're going to put a fault on this bus now, and what we've done here is we've done exactly what we've said before. We've got a 51 milliseconds, so we've got a fault on the load side of this breaker in the cable compartment, and we've only isolated this breaker, feeder number 1. We didn't open feeder number, the main coming in. So we're at 51 milliseconds and 3.03 calories per centimeter squared. And the difference is we're using the Sentry relay. And with the Sentry relay, we can put a fault, place a fault or a site sensor in the cable compartment and only open the local breaker. However, if that fault was on the main bus, we would have to open up the main breaker. So if we put a fault on the main bus and with light only, we have 6.63 calories per centimeter squared, and we still opened in 51 milliseconds. However, with the optical, on the load side of the breaker, we're at still 51 milliseconds, but 3.03. Now, in feeder number 2, I've interlocked the light with the pressure. Obviously, the pressure is going to take an additional 9 milliseconds. So we have 60 milliseconds to clear the fault, and it's 4.228 calories per centimeter squared. And by comparison, feeder number 3 has no protection, so we're going to be relying on the instantaneous of the main breaker to clear that fault. But we've lost everything. We've lost the entire load because we had an arc flash in the load side of the compartment of feeder number 3. So to recap, light is the fastest, but if you want to interlock it with current, then you have to set the current to a level that is below the arcing current that you have on your system. And I hate to do this to you, but that's all there is. Are there any questions?
Hi, Sergio. Yes, we did get some questions. First off, all the questions asking for a copy of the webinar or the PDF of the slides. It'll all be available by tomorrow on our website, www.i-gard.com. As always, I will email you the link so you can just check your inbox and easily access that. Now on to questions for Sergio.
Okay, Jessica, please inform them that I cannot share the single line because it was shared with me and by ETAP, and they made me promise my firstborn, and seeing as he's 30 years old, I gladly gave him to him.
Perfect. Okay. Sergio, do the Sentry and the MGFR have the same cutout size? If not, is there a plate or anything of that nature to fit the Sentry into the existing cutout?
Right now, the MGFR is a panel mount, and the sentry can be mounted on the back plate, but we have a communication module that that can communicate with the MGFR that can accommodate the same cutout.
Okay. Are the sentry and ADM output contacts fast switching? How fast do they operate from the moment of an arc event to signal output?
Less than 1 millisecond.
Okay. What is the significance of light and pressure? Also, is a light and current combination possible?
Light and current is possible with the architect, and we have used the architect with light only and light and current. With one particular example, I can try to show you here. Anyways, while I'm trying to find that one. Obviously, light and current is going to take a little bit longer, not a great deal longer, but a little bit longer, and you're going to sacrifice a little bit of time. And then, as we said, time is directly proportional to incident energy. Light and pressure, it's actually pressure differential. So you're looking at pressure differential from the inside of the chamber to the outside of the chamber. And that takes an additional 9 milliseconds. But what we want to do is we want to ensure that the light is reinforced to have an arc flash with the either current or pressure. The problem with using light and current sometimes is if a circuit breaker is performing its duty in clearing a through fault, then you may have the possibility of having the light coming from the arc chutes and the current, because you do have a through fault, operate the arc flash relay. And here's an example of the architect being used with 12 point sensors and a point sensor going to a fiber sensor. So these were protecting a massive transformer, rectifier transformer, and we opened up the primary breaker when that happened. So because it was a rectifier transformer, it was difficult to use light and current, so we had to use light only. Okay. Sorry, Jessica.
What happens if the local circuit breaker is not shielded and we need to trip the arc using an upstream breaker?
You can have, the architect has a backup relay, which you can trip the upstream device. With the Sentry, you can also trip the upstream device using the same contact.
Okay. What is the response time of the architect using both light and current?
It's about 4 to 7 milliseconds.
Okay. What is the voltage input for the Sentry?
Power supply, you mean? It's 120, 240, or 85 to 250 AC DC, and we can have 24 volt DC or 48 volt DC or 125 volt DC. It's very flexible. We have a wide range, which is one of the main reasons we did this, because we had a 240 volt MGFR, and the transformer was getting larger, so we were unable to market 240 volt MGFR, so we changed it to a universal power supply and put it in a more modern enclosure.
Do the ADM pressure sensors act to confirm the arc event, the light detection followed by pressure wave? Does the ADM operate if one or the other, being pressure and light, is not present?
You can configure it so that both have to happen or either have to happen.
Okay. What type of cable is wired to the Architect relay?
We have point sensors, but we also have modules that convert this input to fiber. So you can go directly into the relay with fiber. So it's very flexible. And we have the open core and open clad and clad type fiber that we can use. And the unclad fiber is basically sometimes used for the main bus. You can cover a wide area with the open clad fiber to detect an arc flash.
Okay.
So you can use both the point set, the wire and the fiber that can come directly into the Architect.
Great. Okay, next question. What does AFD stand for?
It's an adjustable speed drive. Was that in my presentation?
I don't know. AFD. If we can get to this one on the in the Q&A booklet that will be distributed next week. Perhaps there is a typo in this question. Can we test the pressure relay mechanically during the commissioning?
Yes. A portable air compression chamber. You know, you use these things to basically clean off the keyboards with the that can be purchased anywhere, and we can regulate the pressure coming out so that you can see where it triggers.
Okay. I think that we are actually coming to the end of the questions that we have received. Oh, we got one more. We'll do this one and then wrap it up, as I think that, like I said, we've got to most of them. Is it true that the arc flash relay will pick up on arcing current, whereas instantaneous, depending on the setting, will pick up on three-phase bolted fault?
Well, when you're going to interlock your arc flash relay with current, you do want to ensure that you do have an arc flash, so you're going to set your pickup to be below the arc flash available current, arcing current. Instantaneous current, you still need to coordinate your system so that you can operate downstream devices. So I think the answer to that is yes.
Okay. We received one more. Is a special light source required for testing these relays?
There are test benches out there or test equipment that can actually produce a light source and a current to simulate an arc flash, and you can measure the time it takes to detect the fault. It's easy for us to do in the lab because we measure when the arc flash is detected with the light and the output, and we can measure that time, unfortunately with oscilloscopes, to determine the timing of the operation. And again, this was a very simple topic, and I don't think I don't know if I did it justice or not.
Well, thanks to everyone who submitted questions. If we somehow missed yours by mistake, don't worry, we will be releasing the Q&A document a week from today. That'll be emailed to you, or as always, it'll be available on our website along with all the other Q&A documents and recordings from the past 4 webinars that we've done. Feel free to continue submitting questions for the next few minutes. And also there should be a webinar satisfaction quiz that pops up where you're able to provide us with some feedback for how we can improve our next webinar. Sergio, anything else from you?
Yeah, I was just reading the question. AFD means, it says arc flash detection. So I'm not sure where I use the AFD. I'm trying to look here, and I have AFB, which is arc flash boundary, and this is measured in feet. FCT is fault clearing time, unless it's the ADM, which is arc detection module. So I'm not sure where I use AFD, but I'll look through it, and then obviously I have to correct how I spell discrete.
Yeah, there's a few comments here saying it stands for either arc flash device, or maybe someone else heard AFB because we have arc flash boundary coming in. But either way, we'll look through and confirm in the Q&A released a week from today. That's it, everyone. Like I said, we'd love it if you do the quiz that will pop up at the end of the webinar. You can let us know your comments or requests for topics and things like that. So thank you for attending. Continue to stay safe, and hopefully you will join us in 2 weeks for our next webinar. Anything else from you, Sergio?
No, I'm good. Please, everybody stay safe and stay well.
Okay. Thanks. Have a good afternoon, everyone.